Hello guys, welcome to Yebo Physics on a Wednesday afternoon. My name is Arnold and I'm going to be joining you this afternoon. And we are going to be interacting together while we're solving physics problems. So today we wish to look at questions on tutorial 7. That is for the PHY V101 group, where we're going to be looking at problems on oscillations and some problems on universal law of gravitation. So that is what we intend to look at this afternoon. And for those doing FVV101, we're going to be finishing up on the problems that are on chapter 14, section 5. So there are a few problems that we hadn't gone through, which we are going to cover this afternoon after we have looked at the set of questions that are on the PHYV101 model site. And apparently the concept is still relevant. The concept that we're going to, or the questions that we're going to be looking at on the model site for the PHYV 101 is the questions are still of relevance to those also following FVV 101, because you still are going to be looking at oscillations and wave motion. So this will still add to your learning. So I hope you guys are going to join in and interact as we solve problems together. It's good to have your participation on our channel, and it's good to get questions and contributions from you as well. So for those that are following on the YouTube channel, you can use the chat box to communicate with me, and those who are following live on Teams platform, feel free to unmute your mic if you wish to, or you can type if you like on the chat box. We'll be able to see your comments and your contributions as we are going through the tutorial session together. So let's get started. We want to start with the PHYV 101 questions. That is question 1. Teams platform. All right, so the very first question that we have, which is already shown on the screen there, it says there are 3 uniform spheres of masses M1. Masses M1, which is equals to 2 kilograms, and M2 4 kilograms, M3 6 kilograms, are placed at the corners of a right triangle as shown in the figure. Calculate the resultant gravitational force on the object of mass M2, assuming that the spheres are isolated from the rest of the universe. All right, so that's an assumption that we're going to take note there. So we have been given 3 spheres, or 3 masses, M1, M2, and M3. And there is a sketch that is going to help us. All right, so the force F12 is an upward force, which is the force between M1 and M2, and the force between M3 and M2 is a negative force, or it's in the negative x direction, while the force F1 on 2 is in the positive y direction, which is in the positive j direction. So the universal law of gravitation from Newton's law of gravitation states that between any 2-point masses, there is a force, and its magnitude is directly proportional to the product of the masses of the 2 bodies and inversely proportional to the square of the distance of separation, which is the equation that we have already written here. So what else do we need? So we then make F2 to be our reference. If we've done this, then we make F2 to be our reference. It becomes our reference position. And then we can calculate F1 on 2 and then calculate F3 on 2. Why on 2? Because that is our reference, because we've been told to calculate the resultant force due to this point mass on M2. So we're taking M2 as our reference. So our resultant force, which we're looking for, F will be equals to the magnitude of force 1 on 2 plus the magnitude of force F3 on 2. So we are then now going to calculate independently F1 on 2 and F3 on 2. Then we sum these two to get the resultant force acting on the mass M2. So let's get on it. So this is the equation that we're going to be using. I've already mentioned that that is the equation that we're going to be using. So F1 on 2 will be equals to M1. Okay, let me put the constant G. So it's going to be G M1 M2 over R1 2 all squared, and which is going to be equals to 6.67 times 10 to the negative 11, and M1 is has been given, and I have to check the value for M1. Value for M1 is 2 kilograms, so it's going to be 2 times M2, which is 4 kilograms. 4 kilograms. Then we divide that by the square of the distance of separation, which is a distance of 3 meters. 3 meters. So that's the y coordinate that we've been given, at which M2 is seated. We can see, no, at which M1 is seated. We can see that M2 is at the origin, which is 0, 0 coordinate. So the distance in between becomes 3. Then we square. Then on the other end, we calculate F3 on 2, which is equals to G M3 M2 over R3 2 all squared, according to our equation. When you substitute this, now we should now take into account that we're calculating a vector F3 on 2. According to the diagram, we can see that it's on the negative x direction. So we're going to put the negative, then the constant 6.67 times 10 to the negative 11 times M3. M3 is 6 kilograms and M2 is 4 kilograms. And in this case, the distance of separation is okay, so it's going to be 4 meters, because the M2 is at the origin and M3 is at an x coordinate, which is -4. So the distance of separation will be 4, like that. So now let's use our calculator to then punch these values that we have here. So this is going to be, so the first one will be 6. Times 2 times 4 equals to that. Then we divide that by 1 over 9. Okay, so we'll get 5 points. All right, probably let me just do this. Start with a fraction. Right, that looks better. That will be 5.93 times 10 to the negative 11 newtons, and this is in the J direction. Okay, then let's do the same and calculate for the other force. Is this right? Is this right? Is this right? So that becomes okay, 1 point, okay, which is the same as negative 10 times 10 to the negative 11 newtons, and this is in the I direction. All right, so we said our resultant F is equals to F1 on 2 plus F3 on 2. Okay, so now we can then add the 2, which is 5.93. So yeah, 5.93. Okay, this is the J. We can start with the I, which is negative. The I is negative 10 in the I plus 5.93 in the J times 10 to the negative 11 newtons. So this is our force, which is our resultant force that we have been asked to find. So let me know if you have got any comments regarding how we've calculated this problem. So we first had to find our reference, and our reference was M2. We calculate the force F1 on 2 and the force F3 on 2. Then after that we sum to find the resultant. So basically that is how we've solved this problem, and we have made use of Newton's law of gravitation, or the universal law of gravitation. F is equals to gmm over the square of the distance of separation. So that is how we've solved this problem. All right, so if there are no questions, then we are going to continue. To the next question. Continue to the next question. And what is the next question saying? So question 2 belongs to practice quiz 8. So I'm going to skip question 2, 3, and 4, which belong to the practice quiz in tutorial 8, because you'll be having a semester test next week, and it's not going to be on that yet. So we're still going to cover the questions 2, 3, and 4 next week in the next coming tutorial, when we're now looking at tutorial number 8. So let's look at some questions on oscillations. Yes, oscillations. Right, so a body oscillates with simple harmonic motion along the x-axis. Its displacement varies with time according to the equation x is equal to 5 sine open bracket pi t plus pi over 3. Right, so let's write down the equation that we're given. So x is equals to 5 sine pi t plus pi over 3. Okay, and this equation looks similar to the general equation which we say x is equals to a sine omega t plus the phase offset. All right, so that means that our amplitude is 5, angular velocity is pi, and our phase offset is pi over 3 radians. So this is in radians, okay? And our phase angle is pi t plus pi over 3. And what is the question requiring us to find? So the question is asking us to find the velocity in meters per second of a body at t is equals to 1 second. So this is at t equals to 1 second. So how do we go about this question? So we do not have an equation relating to velocity, but we've been given the displacement time. So displacement time, that is what we're given. So we're given the displacement time. So from your knowledge on kinematics, you know that given a displacement time graph, you are able to determine the velocity by differentiating the displacement time graph or the displacement time equation. If you differentiate the displacement time equation, you find the velocity. Or if you calculate the gradient of a displacement time graph, you will get a velocity. So in this case, we've been given an equation which relates to the displacement time, meaning that if we differentiate that expression, we should be able to find an expression for a velocity. So why? Because if you say dx over dt, this is the change in displacement over the time, which gives you the velocity. So if we differentiate this expression, we should find an expression of velocity with time, and we can then use that expression to calculate the velocity. All right, so how about we get on to that? So we're saying x is equals to 5 sine pi t plus pi over 3. So if we say dx over dt is equals to, so now you ask yourself, if you differentiate sine, what did you get? You'll get cos, right? So this will remain as 5 cos pi t plus pi over 3. And using the chain rule, this will be d over dt pi t plus pi over 3. All right, and this will simplify to dx over dt, which is equals to, differentiate that expression, it will be pi. So that will be 5 pi cos pi t plus pi over 3. Okay, and what are we looking for? The velocity. And we have said that dx over dt is equals to velocity. So this means that our velocity is equals to 5 pi cos pi t plus pi over 3. That is our expression to find the velocity. Now we can punch this. So this is 5 pi cos pi 1 second plus pi over 3. So now all we need to do now is to punch that. All we need to do now is to punch. So now let's punch that. 5 pi cos pi plus a fraction that is pi over 3. Okay. So we get 15.6. If you check the calculator, this is in degrees. So we have to convert this to radians because our phase angle is in radians. So we should change that to radians. So make sure when you are dealing with these problems, your calculator is set into radians. So that will be equal to negative 7.9. Negative 7.9 meters per second. So that is how we're supposed to work that out. All right, so that is how we're supposed to work it out. So basically we just differentiated that expression. Differentiate that expression to then get the velocity time expression, which we can then use to calculate the velocity. Let's move on to question 6. It reads, a body oscillates with simple harmonic motion along the x-axis. Its displacement varies with time according to the equation. X is equals to 5 cos pi t. The magnitude of the acceleration in meters per second squared of the body at time t is equals to 1 second is approximately. So we've got a lot of options that we have there. So we start by writing our equation. X is equals to 5 cos pi t, which is identical to x equals to a cos omega t. So now, to break down that question, we're given a displacement time expression, and we now know that having a displacement time expression, you can differentiate that expression and obtain a velocity time equation. All right, and our knowledge again from kinematics, if you differentiate a velocity time expression, you obtain acceleration time expression, which is the same as if you have a velocity time graph, you are then able to calculate the gradient of the velocity time graph and obtain acceleration. So this is exactly what we're going to do. So this is going to be like a second derivative of the displacement time graph. The second derivative of the displacement time equation will then give us the acceleration time expression. So we'll differentiate the displacement time equation to get the velocity time expression. Then we differentiate that expression again to get the acceleration time equation. So that is exactly that we going to do in this problem. So essentially what we're saying dx, and put it here, dx over dt is equals to v, and dv over dt will give us acceleration. All right, so dx over dt is equals to 5. If you differentiate cos, you'll get negative sine, right? So that will be negative sine pi t dot d dt of pi t, and this will be negative 5 sine if you differentiate this expression, take out the constant, so it's going to be 5 pi sine pi t. So this is our dx over dt. The second derivative will then give us the what? The acceleration. So that will be d squared x over dt squared will then be equals to, if you differentiate sine, you get cos. So the negative sign is still maintained. So that will be cos pi t dot d over dt pi t. If you do that, that will be negative 5 pi squared cos pi t. So this will be our d squared x over dt squared. And our second derivative, we said d squared x over dt squared is equals to our acceleration. So acceleration is equals to negative 5 pi squared cos pi t. Let me know if you're following, guys. Let me know if you're following. You can put your comments in the chat, or you're on Teams, you can unmute and share with us your comment or contribution. Now, if you've done this, our problem has been solved. So all we need to do now is to punch. All we need to do is to punch that. What is our time? By the way, it's 1, right? So it's going to be pi. 5 pi squared that. So it will give you 49.3. which has been, okay, we have an option there, which is 49, so that's that. Right, so that is how we've solved this problem. So we took the second derivative of the displacement time graph. Okay, which is what we were given in the question. So I hope you are following on how we are solving the problems on simple oscillatory motion. Let's quickly move on to question 7. I don't see any questions on the chart yet. The question reads, a body oscillates with simple harmonic motion along the x-axis. Its displacement varies with time according to the equation given the question. Then we are expected to calculate the phase of the motion. Right, so let's write down the equation given. X is equals to 5 sine pi t plus pi over 3. And we've said that this is similar to x equals to a sine omega t plus pi over 3. And this is our phase that we're expected to calculate. And we're given that, what's the time? That is at t is equals to 2 seconds. T is equals to 2 seconds. So if you look at that expression, we have got, so by inspection, our angular velocity omega is equals to pi. By inspection, our angular velocity is equals to pi. And we've been given that t is 2 seconds, and now we've got our angular velocity. So what's requested of us is just to sum that up. So because we're saying phase is equals to omega t plus, oh, I'm supposed to do, so this is, okay. So, and in this case, we've got pi t plus pi over 3. So what do we have? Our pi is pi, that's 2 plus pi over 3. So this is just 2 pi plus pi over 3. So are we giving it in terms of pi here? So it will be 2 plus 1 over 3. 2 plus, which is 7 over 3. So this is 7 pi over 3. 7 pi over 3. And this is in radians. In radians. So that is how we've solved that problem. That is how we've solved that problem. I hope it's clear. All right, we have another question here on question 8. Okay, and this is y, and that is obviously the y-axis is representing the amplitude or the displacement, and this, the maximum displacement is our amplitude. Now what does the question says? Which of the graphs below shows the wave where the amplitude and the frequency are each reduced to half? So if the amplitude was at this point, so for the next situation we expect it to be halfway below there. Then this is a graph of displacement versus time. So what do we know about frequency and period? So the frequency are each reduced. So if we reduced the frequency, it means the period should increase. The time taken to complete one oscillation will be greater. So if this was completed in 2 seconds, which means at 2 seconds for the new graph, we will be halfway. We would have completed half the oscillation. Okay. So I'm going just to put this. All right. One. Yes. That's halfway. So let's see. Graph A, the first graph, is exactly similar to the one that we have, so we can eliminate that. Graph B, the amplitude has actually doubled and the period did not change. Then graph C, the amplitude has reduced to half, which is what we want, but the period did not change. So C is out. Then D, we see that for D, the amplitude looks the same. No, it doesn't. Yeah, it looks the same, meaning it hasn't changed. So this is not what we want. The amplitude should actually change. The amplitude should actually change. And for the next graph, we see that the amplitude is halved and also the time has also reduced. So, which is what we were talking about to say amplitude be like that. So something like this. Why are we doing that? we see that if you look at the graph up to this point where I'm going to put this green star, this was one complete oscillation for the initial case, right? It was one complete oscillation. So if we then increase the period, increase the time taken, which means that at this time where we had a full oscillation, we'll now be having half an oscillation because the period has increased. The frequency has reduced. So the initial graph could complete one oscillation in a given time. Then the new graph now completes half an oscillation compared to the first case scenario. So in this case, we've reduced the amplitude and increased the period. Remember, the period is the time taken to complete an oscillation. I hope this makes sense. Let's look at question 9. Question 9 reads, a 50-kilogram satellite circles a planet Krypton every 5.6 hours in an orbit with a radius of 12 times 10 to the power of 6 meters. What is the magnitude of the gravitational force on the satellite by the planet? Okay. So this is orbiting, right? Okay, yes. So okay, and we've been told that this distance is 12 times 10 to the power of 6 meters. What else are given? The period is equals to 5.6 hours, which is equals to 5.6 times 3,600 seconds. That is the period. And what else are we given? And what else do we know? Okay, the mass of the satellite is 50 kilograms. Is it? Yes, it's 50 kilograms. That's what we are given. So this is the center of our planet, and we should remember that F, due to 2-point masses, G is equals to mass of the satellite or mass of the planet times the mass of the satellite over r squared. All right, and we should also recall that because we have this satellite orbiting, Fc is equals to the centripetal force, which is m v squared over the radius. All right. And remember, this is what we have. And our Fg is equals to our Fc. So now, with what we have, remember V is equals to omega R. So which means to calculate our gravitational force, we can then use the expression F is equals to our mass of the, okay, this is S, the satellite, V squared over R. This becomes M. In place of V, we put omega R. We square that all over R. That becomes M omega squared R squared over R. You cancel that, you cancel that. You will then be equals to M omega squared R. That would be your force. And the mass is 50. And angular velocity omega is equals to 2 pi over the period. It's something that you should recall. So this will be 50, 2 pi over t squared times the radius. So this would be 50 times 4 pi squared R over the period squared, which is 5.6 times 3,600 all squared. Don't forget to square, because this expression is just equals to 15 times 4 pi squared R over t squared. And this is our t. We just have to square it. Now what remains is for us to then punch that. Got to put the value for the radius. It's 12 times 10 to the power of 6. So it's times 12 times 10 to the power of 6. We get 58.2328. Right, so that is what I'm getting there. Check. So indeed, that is what we are looking for. So this is just a concept taken from the relationship between the universal law of gravitation and motion in a circle, or the centripetal force. Okay, so that is how we work that out. So these are the questions that I wanted us to look at on the PHYV101 questions. So the remainder of the questions you will go through them with Lucian on Friday. So these are the remaining questions that are there. Now, as I mentioned earlier on, that we're also going to be looking at the questions on FVV 101, which is chapter . Okay, so these are some of the questions that we are supposed to look at for those that are following PHY FVV 101, and these questions still also are of good importance to those that are following the PHYV 101, as we're going to be looking at some questions that involve static equilibrium and so on. So question 8 reads, a person working at a drafting board may hold her head as shown, requiring a muscle action to support the head. The three major acting forces are shown. Calculate the direction and the magnitude of the force supplied by the upper vertebrae, which is Fv, to hold the head stationary, assuming that this force acts along a line through the center of mass, as do the weight and the muscle. All right. So we're going to put a sketch. So this is our center of mass, and we've got the weight equals to 50 newtons, and we've got this force that we have there, which is Fm equals to 60 newtons. Okay, and we are to get this resultant force. That's theta, and this is a Fv. So if we were to form a Cartesian plane, we would have something like that. Okay. So essentially what we need is the resultant of these two forces that were given, that is the weight and the Fm. Okay. And remember, if you to find a resultant, Fr is equals to the square root of the summation of forces in the x squared plus the summation of forces in the y squared. Okay, so remember always that if it's a system that is in an equilibrium, then summation of forces should add up to 0. All right, so we see that Fm has a component in the vertical and a component in the horizontal. So if you are to form a right angle triangle, which is what we were doing in vectors, this will still be 33 using your knowledge on set angles. All right. So which means that FM or let's start the X will be equals to 33 cos, right? Yeah, 33 cos 60. No, 60 cos 33, because this is the magnitude, which is 60 newtons. So it's going to be 60 cos 33, whereas FMY is going to be 60 sine 33. And FM in the Y is negative. And 50 newtons is also in the negative direction. Now let's find the sum of forces. Sum of forces in the X is only 60 cos 33. Then the summation of forces in the Y is equals to negative 50 minus 60 sine 33, which is the same as negative 50 plus 60 sine 33. However you want to represent it, but it's negative because we are on the negative part of the Cartesian plane in the Y direction. So now we move on to that. Our FV will now be equals to sum of forces in the X, 60 cos of 33 all squared plus a negative 50 it's going to be 50 plus 60 sine 33. Even if it's negative, when you square it, it's going to be positive. Right, so the next thing that you do now is punching. Cos 33, change that to degrees. 16 cos 33 squared plus 50 plus 60 sine 33. Square that. Get 96.7. Which is what we were expecting to get. Right, now having obtained your finding the angle should not be difficult, so you satisfy yourself that the angle should be 59. We have done this a number of times, countless problems that we've solved on vectors requiring us to. So you see the importance why we were emphasizing the vectors tutorial. So we always need to use this knowledge on many other concepts. Then question 9 is another question on static equilibrium. It says even when the head is held erect, its center of mass is not directly over the principal point of support, but the muscles at the back of the neck should therefore exert a force to keep the head erect. And that is why your head falls forward. Okay, when you fall asleep in class. Interesting. How many have fallen asleep in class. I, for one, I have. Calculate the force exerted by these muscles using the information in the figure. What is the force exerted by the pivot on the head? Okay. So the first thing that we need to do is to put up a sketch. Right, so we have our pivot. So this is Fm. This is the weight equals to 50 newtons. That's a 5 kilogram head. Then we have Fj. Okay, so this is 0.05 meters. And this is 0.025 meters. So remember, sum of torque because this is in equilibrium. So we're taking moments about our pivot there, and by so doing we eliminate the force Fj. We remain with two forces. One of them is unknown and it's apparently the one that we're looking for. Right, so our sum of torque should add up to 0. Now let's add the torque due to Fm. So if we extend there, this one is going to be anti-clockwise, therefore it's going to be positive. This one is going to be clockwise, therefore it's going to be negative. So that means that Tm minus T due to the weight, or torque due to the weight, is equals to 0, and this will be equals to the weight. And remember, this is equals to Rf sine of theta. And let's look that our angles, they are all at 90 degrees. So this is going to be R M F M sine 90 equals to R weight F to the weight sine 90. Sine 90 is 1. And we're looking for Fm, which is R due to the weight F weight over Rm. So that will be equals to R to the weight, that's 0.025 times 50 all over m, Rm, which is 0.05. We punch that, what do we get? Okay, 25 newtons. So Fm is 25 newtons. 25 newtons downwards is shown on the diagram, okay, which is exactly what we're expecting again in that. Then we should find the force. So this was part A. Force exerted by the pivot on the head, which is our Fj. So for a system in equilibrium, remember that the sum of forces should add up to a 0. So in this case, all our forces are in the y. So Fj is the only force in the positive, minus Fm minus F due to the weights add up to 0. So which means our Fj is equals to Fm plus Fw. So that's 7, what? That's 15. 25 plus 50, which is equals to 75 newtons, which is our Fj. And according to the diagram, we see it's going upwards. And this is exactly what we are being asked to find or to obtain. All right, so that is it on this particular question. All right, we find ourselves in having another similar case. That is question 10. I'm going to read it out. It says a man stands on his toes by exerting an upward force through the Achilles tendon, as in Fig 9.41. What is the force in the Achilles tendon if he stands on one foot? Okay, so which means the entire weight of this person is being supported by that. Okay. Calculate the force at the pivot of the simplified lever system shown, that the force is representative of the forces in the ankle joint. Okay. So we can put up a sketch as shown. And I've got our Fn. Okay, this is so this is a similar case again, where we should recall that sum of torque should add up to a 0, and we've got two unknown forces, two forces and one unknown, so it becomes easier to solve this particular problem. Okay, is there anything else that we're given? Yes, we're also given Fp. So if we take moments about the pivot, we would have eliminated the force Fp. All right, if we extend this, we'll go clockwise, therefore it will be positive. Is it? No. Negative. This will go anti-clockwise, so it will be positive. Okay, so that means that the torque minus A will be equals to 0, and we're looking for A, so this will be just the same. So this is going to be Ra F sine theta, which is equals to R N F sine of theta. That will be Ra F sine of 90 equals to Rn F sine of 90, meaning that this will cancel, that will cancel. This is our A, this is our A, this is our N, and our FA will be equals to RN FN over RA. That means we substitute now. Our Rn is 0.12 and our Fn 75 kg men. So that's the weight of that person. So that becomes 75 times 9.81. Then Ra is 0.04. Then we punch. We get 2000. Which is the same as 2.2 times 10 to the power of 3 newtons. Okay. Which is what we're expected to get anyway. Right, then part B. So this was part A. What does part B say? What does part B say? Part B says we should find the force at the pivot. So we're looking for FP. All right, so remember that the sum of forces should add up to a 0. Sum of forces should add up to a 0. And in this case, it's only the Y. So that is FA in the positive plus Fn in the positive minus Fp to a 0. Therefore, it means Fp is equals to Fa plus Fn. And our Fa, we obtained it as 2207 plus Fn, which is 75 times 9.81. So we can sum that up, right? As plus that's 2943. And according to the diagram, it's a downward force. All right, so that is essentially what we were expected to do. So we have literally covered all the questions that are, or that were on section 14.5. If you missed the other questions, so today I started on question 8. If you look at the previous video that we recorded last week on Thursday, it covers the questions 2 up to 7 on section 14.5. So if you've missed, if you probably have missed any of the questions that are in section 14.5, question 2 to 7, you'll find them in the previous recording that I had on Thursday last week. So if there is a question of interest that is in section 14.5 on static equilibrium, on static equilibrium, you'll find the question. It's there in one of the recorded videos. So this is exactly what we intended to cover today, this afternoon, and I hope that this will add to your learning. So make sure on Friday you tune in for the remaining questions on FVV101 tutorial 7, where we'll cover the remaining questions, that is from question 10 up to 15. There are some interesting questions that are there, so ensure you join in the live session, or at least you follow the recording afterwards. Otherwise, from myself and everyone in the studio, it's a goodbye. Remember to keep on practicing. By practicing, you sharpen your problem-solving skills, and all the best in the next coming semester test. I believe if you follow these tutorials and you follow your lecture notes and you practice, do discussions as well, you'll do quite well in your semester tests. And feel free to reach out if you've got or if you're experiencing challenges in conceptual understanding or in problem solving. Feel free to reach out to any of the Able Physics tutors who will be able to assist you, okay? So it's a goodbye from me. Cheers, stay well, and take care.